entirely sure what this is that you're watching right now, and I make ASMR, so that's saying something. Sat down to a traditional but unconventional for me breakfast. Some steak and eggs. Trying this new keto thing out, and it seems to be working pretty well, at least, if not burning fat and ketosis. It's just making me much more conscious of not eating processed foods and sugars. So that's some net positive. But I'm trying to do as much research as I can, because I've always had a thing for space, as you guys know by some of my videos. And I went to the library and checked out some really, really great books. This is by far my favorite. It's more of a chronology of major milestones in astronomy, starting from the most ancient observations and estimations of characteristics of the universe, all the way to the rise of astrophysics, and extrapolating that into the triumph of technology, which led to things like the Hipparcos and the Hubble and Gaia satellite observatories in orbit. My current episode here, and look at this thing of beauty. I gotta admit, I've always been a Windows guy, but Molly just bit the bullet and bought one of these because she has an iPhone and just knows how much, how synonymous with the quality, Apple products are. So I'm pretty frustrated with my Asus as a quick tangent, and I may be getting a MacBook if I can afford one sometime soon, as soon as that thing fully breaks down, because the touchpad and the backlighting, and sometimes even the touch screen that I bought it for doesn't even work. But rant over on the Asus. Poor craftsmanship. So I have this just in case I want to research slightly more in depth, or use the ever useful. Look at that. That's brilliant. Love the fingerprint sensor right there. The website Wikipedia is definitely my friend. This is clearly a off-the-cuff video here. If I even post it, maybe I'll post it just to Patreon. But right now I'm currently trying to make a video. I'm using this as my narrative template, and this is the one I base the basics of astronomy off of. And I'm getting the details, so that's my outline, the rough direction that I want to kind of take through this. I'm trying to meander, obviously, like I am with this video, but astronomy in general, cosmology and physics, and all of the science that defines what we know about the universe. There's a lot of it, and it's kind of a lot to wade through, especially me knowing very little. Taking a couple of physics and engineering courses, I have my toes wet, but so I understand in regards to some of the basic conceptions, like spectrometry, for instance, how light gets broken up into, look at that, I didn't plan that, into wavelengths that are specific that correlate specifically. There's emission and absorption spectra that are emitted from the atmospheres of stars, and they correspond to wavelengths of different types of lights. Wavelengths correspond to color, and that also corresponds to the energy level or the frequency. Lower the wavelength, the lower the frequency, more red it gets into infrared, and less energy it intrinsically is characterized by. So things like that, you know, everybody learns if you took a basic physics course in college. You usually do a lab or two on that. And lived on page 200. I lost the wheel there. But anyways, I'm using this book as like a nice reference. And Starbirth is the episode I'm researching right now. So I'm trying to get my fats and proteins in with some vitamins. Hi, Susie. I got my dishwasher over there. And since I'm moving the camera, there's my, what would I call him? I'd say he's probably my fitness instructor. He's certainly giving me a run for my money. He's the guy I go run and bike with. So Susie's the one I read and watch TV with. Okay, so now that my meal is nice and cold, let's try to delve a little bit deeper into astronomy. And it's kind of it's a little bit of a task for me, because you okay? She's okay. She does have a little personality on her. Alright. So, Starbirth is, you know, I love involving the history, because what I really don't like about these very mainstream, very loud, very CGI heavy, you know, poor CGI oftentimes, very basic. Hi, big boy. Hey, big boy. Yeah, I might let you clean my plate later. My biggest issue with mainstream communication of these ideas that I'm learning about, especially since they're given by you know, scientists, a lot of them at the forefront of the exploration and you know, of these fascinating subjects and science, subfields of science. They don't seem to be, so they're highly intelligent people, but they seem to dumb it down to a point where they're patronizing the audience, and they're using analogies and metaphors that, you know, to me are uninteresting. I mean, I love the idea of Eric Weinstein, who has his own podcast called The Portal now. He's a mathematician and physicist and just an all-around intelligent dude. And he makes a great point that people... Hi there. I hear you. That people don't need to be catered to. They you know, we thrive off challenge. If someone's genuinely interested in You know, if we want to learn something, I think it's oftentimes more stimulating and entertaining to be shown ideas and exposed to ideas that are beyond your limit of understanding, as long as the expert in the field can guide you to pathways that might help you further explore the ideas. Because what a black hole is and what the expansion of the universe is, talking about quantum probabilities, it's really things like are not intuitive, and sometimes trying to describe them in forms of intuitive examples or intuitive analogies rather doesn't really help shed light on it. It just kind of obscures it a little more, because then you have the wrong idea if the analogy is imperfect. So for instance, I rarely hear the distinction of, let's see if we can look it up quick enough. The elaboration of how the orbit of planets can be expressed through calculus. Let's see. The area of planetary orbit, integral, orbital mechanics. And let me give you guys an image, because it's again another thing that Eric Weinstein really a point he made that really made a lot of sense to me was that we are visual learners. Our visual cortex, I think, is I don't know the exact percentage, but it's a significant percentage of our brain. And so why not take advantage of that when learning? And I actually do learn a lot more quickly when exposed to visualizations like this. So this is a pretty good picture right here, if you guys can see. If we consider the black dot the sun, the blue dots around the perimeter circumference there, any given planet, or really anything orbiting another object in space, the filled in lines there, triangles, slices of pie, represent equal areas, or at least they're supposed to. So mathematically, it's fascinating that this actually works. So we can see here, it says a line that connects a planet to the sun sweeps out in equal areas in equal times. So even though these points, these points here are clearly not equidistant apart. These times here are much shorter. The planet, as it gets further away, in the aphelion is the furthest point from the sun, the perihelion is the closest. The orbital mechanics of the planet's orbit around the sun are such that the change in velocity of the planet, and this looks closer to like Mercury's orbit. Earth's orbit around the sun isn't as eccentric of an ellipse, but it still is not a circle. It still is an ellipse. So we do have one part of our orbit that is closer to the sun, and during that, the planet Earth is speeding up. It is actually moving faster, objectively, around the sun at that point than it is out here, where you can imagine it slows down. Something always in free fall like that would slow down at its aphelion, and then as it comes closer and closer towards the sun, it begins to speed up and it kind of gets whipped around. But it's interesting that it works out mathematically, that if you come up with an equation for the distance between these 2 points, the integral which generally, for any equation, an integral of it is going to give you the area. Let's see, integral area. It's going to give you the, no, this isn't a touchscreen, one downside. It's going to give you the area, so here you go. Here's a nice clean example right here. When you integrate an equation like this, y equals f of x, general equation, the integral, the answer that the integral spits out is the area under that equation. So in the same way, I love that idea that the integral of the equation that defines the Kepler equation, you know, that defines Earth's orbit, is going to also say that there's an intimate link between maybe the slower time it takes here is equal, its integral is equal to the quicker movement, so the slower velocity rather, to get to move across, say, 10 days here, its integral is going to equal, although the speed is slower and this speed is faster, the integral is going to equal the same. I know that doesn't make complete sense, but yeah, it's just really interesting. The I don't know, it's interesting to me that mathematics can enlighten us so much about the laws of the universe. And, you know, while obviously I'm no mathematician and physicist, I do like trying to at least probe as deep as I can underneath these superficial explanations and very tabloid style astronomy documentaries. I just don't really care for them. So, so for instance, when I'm looking at the star birth, it's interesting that I guess I don't really have a point to get to, but it is interesting to piece together as many topics and you know, historical revelations and breakthroughs, scientific observations and intuitive ideas that were you know, inductively arrived at. Such as, you know, Kant. I love just making a synthesis of everything to give me a whole big, broad picture, and not just, you know, well, I don't know, you know, something happens because it does, and it's amazing, and then they have a big, you know, own sound effect with some underwhelming CGI to go with it to prove their point that. Actually, I need some coffee. A little bit cold, as you can tell. You know, that the talking head, the present expert on camera, is correct. So, anyways, books like these are still priceless, you know, to me. When trying to learn as much as I can about it. Until the late 1940s, it was not known where atoms of most elements came from. You know, carbon, oxygen, iron, or how they'd been made. So it had been established in the 20s that the two lightest elements, hydrogen and helium, made up most of the universe's matter. And in 1948, George Gamow and Ralph Alpher, that poor guy, Ralph Alpher showed how all the hydrogen, most of the helium, shame on his parents, by the way, for naming him Ralph, and a tiny amount of lithium could have been made in the Big Bang. However, the origin of most of the heavier elements than that was still a mystery. Building to iron. So the discovery of their origin was made largely thanks to the work of British astronomer Fred Hoyle. Born in Yorkshire, England in 1950, attended Cambridge in 1933, got a degree in mathematics, worked in World War II on radar systems. I wonder if he worked with Alan Turing. He joined about 25 years later. He joined the staff at the Hale Observatory in California and became professor of astrophysics at Cambridge the following year. So he's best known as the proponent of the steady state theory, which didn't age too well, no pun intended. His claims that as the universe expands, the average density is kept constant. So, ironically, he coined the term the Big Bang, but he was an opponent of it, of that theory. And in later life, as a quick side note, he took a particular interest in the presence of organic molecules in comets, which he thought probably brought life to Earth. So, starting with chance conversations with lead astronomers in the U.S. during an academic tour in 1944, he developed the idea that most chemical elements might be created in a step-by-step nuclear reaction in stars, a process called nucleosynthesis. So it's interesting. I mean, who knows? I guess we don't have to, scope to actually dive into the historics of it all, but I'm sure something sparked his mind, like, well, who knows, really, how many steps it might have taken to intuit something like that, but it's fascinating that, up until much less than 100 years ago, we didn't even know what it's taken for granted on all these, History Channel shows today that, most cores of third generation stars are made of heavier metals, So that's so fascinating that the universe, roughly 15 billion years old, first generation of stars, all they had were the smallest elements, because stars, it turns out, are the factories for the chemical elements. Meaning the factories for the chemical elements heavier than hydrogen, helium, and probably lithium as well. So every time nuclear fusion takes place, a lot of other stuff happens. A lot of energy is emitted in formation with Einstein's E = mc squared. But atoms, after, I think I read something like every 20,000 collisions, 20,000, 10 to the 22nd, which is a 1 with 22 zeros after it. So after that many collisions between atomic nuclei in the core of stars, one process of fusion gets actually underwent. And every time, I believe iron is the heaviest element that can be fused in the core of stars, and then all the heavier elements like gold and let's see. Periodic table. So iron is Fe right there. Yeah, so everything, nickel, zinc, I mean, obviously, I don't know nearly as many as I should. Xeon, krypton. Gold. What's the atomic number of gold? AU, AG, that's silver. Silver. Yeah, okay, gold's pretty heavy. Iron. I know, is that iron? Oh, I was looking at nickel. Okay. No, Fe is iron, so that's maybe iridium. Anyways, all those heavier elements that we find on and off Earth, heavier than iron with 26 protons in its nucleus, they're formed through supernova or nova explosions. The pressures created when a star explodes, as its dying last breath, is greater apparently than most or any of the previous pressures in the core of stars that were able to create atoms and fuse them together to get up to 26 protons. And so when we have gold and silver and all these, platinum, all these valuable metals, they're actually, like Carl Sagan said, the stuff of stars. And to the extent that we have iron in our bloods to help certain biochemical processes, it's so fascinating to know that we wouldn't be around to talk about this 13 billion years later if there hadn't been some first and second generation stars exploding and what's the word? Expelling these heavier metals into the rest of the galaxy. Which, on top of the actual material in them, the atoms, we talk about material, the energy of the actual shock often compresses otherwise ineffectual clouds of molecular gas into, it kind of catalyzes them to start moving around, and the more denser areas are going to be where, through a feedback loop, a gravitational feedback loop, more material will start to be drawn towards, and eventually a nebulous proto-stellar area will form, and then when the star forms after enough matter is kind of coalesced in the middle and has created enough gravitational pressure to start the process of fusion in a snap, it blows all the extra gas out, most of it at least. And really, although there is lighter gas like hydrogen and helium left, most of the material that's left, that's not blown away by the solar winds of this baby stellar furnace of fusion that just ignited, is going to be coalesced into the planets as it rotates around over millions, tens, hundreds of millions, even thousands, meaning billions of years. So, back to oil and nucleosynthesis. So he's an English guy. At the end of World War II, 1944, he's touring the U.S. On an academic tour, meaning I guess he's going to different academies, universities, and either giving lectures or being, what do you call them, assistants, visiting professors, I think. And he starts conversing with other people in and around his field of expertise. He kind of starts to develop the idea that maybe heavier elements are formed by the compounding of fusion in the cores of stars. Hans Bethe had already shown in 1939, 5 years previous, that hydrogen could combine to form helium in star cores, but Bethe offered no suggestion about the actual mechanism by which this would happen. So, the cores of stars were not considered hot enough for such elements to form through nuclear fusion processes. Hoyle, however, he thought there could be a process that would sufficiently raise the core temperature of a large enough star. So, 1946, Hoyle showed that in the cores of massive stars, where the temperatures soar to billions of degrees, heavier elements could be made in circumstances called nuclear thermal equilibrium. Such a star would eventually explode as a supernova and eject its heavy elements. In 1954, 10 years later, Hoyle went on to describe how in a massive star that has exhausted its hydrogen fuel, its core would contract and heat up before exploding. And helium atoms would start fusing to create carbon. And so heavier elements require higher temperatures to be created. Suitable conditions. I love how they have little flow charts here. This is brilliant. I love this book. It's very, very accessible. It's got a lot of, pictures, but it's also fairly, it communicates dense material in a very accessible way. So I like that. Suitable conditions for the creation of many elements occur in the evolution of giant stars. So extreme conditions for other elements occur when giant stars disintegrate in supernova explosions. All but a few elements can be created in stars by 8 distinct processes. So it's really only in the last throes of the stellar life cycle, in the most energy-rich, the most violent phenomena, as the core becomes heavier and heavier because the atoms inside it are being compressed into and fused together in the heavier and heavier elements. The core is slowly contracting, and the gravity in a stable star, and stars last for billions of years, so it's got to be quite stable for a long period of time, is offset by the energy, the obviously incredible amount of energy released by these thousands and millions of nuclear, these phenomena of fusing atomic nuclei together, which there's a force that is absolutely opposing this fusion. So it takes, by their nature, the electrons in the outer surrounding the atomic nuclei they repel each other. They do not want to allow the atomic nuclei within them to touch. So it takes an overwhelming amount of gravitational force to be able to overwhelm that. I just said that twice. To be able to overpower, I guess I can't come up with a better word, that electron repulsion and fuse those atomic nuclei together. And the protons themselves, I guess, is really the main repulsive force. The protons are both positive subatomic particles. They don't, just like in regular electricity, like charges always repel. And so there's this stability and there's this balance between the gravitation, you have just orders and orders of magnitude of kilograms of mass, these billions of kilograms of mass, or billions and billions of tons of mass, creating gravity that we haven't the slightest idea of here on Earth. And yet we have all these because of that, we have these atomic emissions as each set of atomic nuclei combine, they release this energy that snaps and explodes and stabilizes the star. So it's this volatile thing that is somehow stable for billions of years, which is really it's no wonder. It's like the more we probe into it, the more it's like it's like Zeus, and it makes sense that it's really incredible how the Greeks had no way of knowing all this, but by making Apollo and Zeus and their strongest gods associated with the sun, which was for obvious reasons, it also is fortified, it's buttressed by the further knowledge of what is actually going on inside these stars. It's like a queen or king that has ultimate power yet ultimate composure at the same time. And so it doesn't release, but occasionally violently has some outbursts. So it's I don't know, it's very interesting to peel back the layers of our historical development and the development of science as well. So, right before the core would contract and heat up before exploding, and helium atoms would start fusing to create carbon. And carbon, we can see here, is an atom with an element with 6 protons in its nucleus. So helium has 2. So helium atoms would start fusing to create carbon. So they might fuse to create lithium and beryllium if one of the protons loses its positron, making it a neutron, and so therefore it's neutral in the atomic nucleus. And when that positron is released, that is, I believe, that makes up much of the energy that we consider characteristic of a nuclear explosion, when it comes to fusion at least. So this could account for the creation of several elements up to iron. And so once iron's created, which has the most stable of all atomic nuclei. So that's interesting. So iron read at 26 protons. And building nuclei heavier than iron would be problematic, since it's an energy-consuming process, whereas creating elements lighter than iron actually releases energy. So there's a threshold at which the star needs energy to be output in order to counterbalance the gravitational pressure directed inward. And so if any elements heavier than iron were created, the gravitational, it would prevent any more stabilization of the gravity. It wouldn't create enough outward expelling of energy because they consume too much energy. And interesting. So it would really, after iron, any elements heavier than that being created and fused, created from fusion rather, would actually simply have a constructive interaction with gravity and allow for the continued contraction of the stellar core. But it says here, there was a flaw in Hoyle's stellar element building scheme. A key step known as the triple alpha process, in which 3 helium nuclei, helium being 2 protons, fused to make carbon being 6 protons, appeared to be too slow, so Hoyle insisted that there must be a mechanism allowing it to happen at a faster pace. And in 1953, a certain property of carbon was discovered that explained it. Look at that. So, Hoyle also explored other processes by which many more elements might be forged in stars. Some of these processes could only occur in the violence of a supernova explosion at the end of a giant star's life. And then it refers us to page 180. Hoyle's work thus explained not only where chemical elements came from, but also how they became dispersed throughout the universe. Yeah, this is so cool. And Fritz Wiki, that was the guy who appeared in Carl Sagan and Neil deGrasse Tyson's new Cosmos series back in 2013. So, yeah, this was amazing. This little diagram here says Hoyle showed how in high mass stars several elements ranging in mass from carbon to iron could be created by fusion. Mass from carbon to iron could be created by fusion reactions occurring at the same time in shells around the core of the star. The number of shells would increase as the star aged. And this diagram shows shells. Here it shows shells with element building reactions in an aging red supergiant. So So in the very core we have oxygen fusing to silicon, sulfur, and other elements. Then neon around that to oxygen and magnesium. And then lighter elements like carbon fusing to neon, and successively lighter and lighter because obviously heavier elements, heavier objects always float and sink, rather, to the center, to the gravitational center of any gaseous or fluid medium. So. And with that, I try to be as graceful as possible, and thank you guys for watching. Look forward to the episode about stellar birth coming soon. Penny, thanks for being exceptionally quiet. You've been a princess, and now you get to lick my plate. Alright, take care, guys. If you're watching this to relax and sleep, you get as comfortable as Ernie.